Hi, everyone, and thank you for joining us today for our live webinar, AIA Certified Continuous Insulation Roofs to Walls. My name is Kim Melton, and I'm going to be the moderator for today's presentation. Before we dive into introductions, I do want to go over a few logistics. The first is that, like many of you, some of us are still working remotely. So if we run into any technical difficulties today, we'll pause the presentation for up to 5 minutes to see if we can address those technical difficulties. If we are not able to do that within 5 minutes, we'll cancel the presentation and we'll either send you a recording or we will send you we'll reschedule it and send you a link to that invite on a new date. Also, we'll be concluding today's presentation with a live Q&A. You should see a Q&A to the right of your screen in a dialog box, and if you click on that, you can submit questions. Now, if you don't see that, across the center of your screen are a series of circular buttons, and the second one to the right is an ellipsis. If you click on that ellipsis, it opens a dialog box with Q&A at the top. Just simply click that Q&A, and it will open the Q&A dialog box for you to use to submit questions. Another important thing I do want to go over is that the information provided in today's webinar should not be used as a substitute for professional engineering design and/or documentation required by codes or contracts or applicable laws. This is for educational purposes today, so please make sure you refer to all manufacturers' specific application guidelines, instructions, and guarantee requirements on all projects. Also, we'll end today's webinar with a survey. This will pop up on your screen as soon as the webinar is done, and we'd appreciate it if you take a couple minutes to fill that out. This survey is your opportunity to provide us with feedback on how we did today. You can use it to ask additional questions. You can suggest new topics for webinars. It's really your opportunity to give us your direct feedback and make sure that we have a two-way street going on communication here. So the survey is also part of how we deliver the JAM experience to you. And the JAM experience is based on 4 pillars of the JAM culture. And those are listed there in the bottom left corner, and that's people, passion, perform, and protect. And we believe it's critical to make sure that we hear, understand, and respond to your needs in order to deliver the best interaction to you, and this survey is how we do that. So with that, I'm going to turn it over to introductions. First and foremost is Joel Asriel, and he is part of our Roofing Systems Division. And Joel, if you want to go ahead and take it from here.
Hi, so thank you for the introduction. My name again is Joel Asriel. I am part of the Specifier Services team at the Roofing Group at JM. I've been with that team for 3 years. Beforehand, I was doing energy efficiency work in commercial buildings. And so it's been a great transition to this, to JM, and our ability to really provide a lot of great technical resources to designers to make roofing or specifying roofing as easy as possible. Thanks.
And my name is Jeff Job with JM a little over 5 years now. Most of my background is actually in construction management, project management. Did that for roughly a decade before coming on to JM, really under the building insulation division with JM focusing more on walls. So we have myself handling the wall portion, Joel handling the roof portion. The presentation is a roof to walls, but we're actually going to start with walls and then move to roofs. So hopefully that doesn't throw anybody too far off, but with that said, we will get going here. I'll point out this slide here really just for AIA credits. Not going to read through all the fine print here, but just to point out the course is approved with AIA for 1 LUHSW credit hour. You can see the course number there in that highlighted bullet over on the left. And of course, this is copyrighted property of Johns Manville. So with that said, we will run through our learning objectives. Understanding thermal bridging. So we're going to kind of run through a number of different examples. And of course, that's kind of the main culprit that continuous insulation is trying to address. So look at those various methods there and how we can kind of remedy those. And of course, defining CI, different types of CI, look at various performance properties related to CI. So talk about the thermal kind of portion, of course, and then we'll dive into some other things related to, of course, air barriers, vapor control, things like that, that when you start introducing CI to a system, it allows you to kind of do additional things beyond just kind of the thermal aspect. Talk about some of the health, safety, and welfare aspects relating to CI systems, kind of again around being able to, how we're kind of changing the temperature profile and the vapor profile of a wall system and how that can significantly reduce a kind of risk of condensation within a wall system. And of course, with condensation, that leads to potential for actual, a lot of different things, but also interior air quality effects, mold and things like that. So we'll get into some of those issues as well. And then kind of move over into, of course, the roof side, talk about various applications on roof assemblies and kind of how those shake out on the low slope systems as well. So with that said, real brief history on CI here. Originated really, I would say, in the early 1900s out of the refrigeration industry. So corkboard was kind of one of the first commonly used materials to create these essentially broad, cover broad surfaces of a wall, right? These continuous, they're looking for ways to kind of, break these thermal bridges, things they can do to beef up the performance of a wall system and find materials that are kind of sheet goods, large surface area. And corkboard was really kind of one of those initial uses. Of course, it's been around in low slope systems for a very long time, and the rigid foam boards really still kind of dominating the low slope market even today. And we'll get into those, of course, later on. And of course, energy code really, whether it be ASHRAE or even IECC, kind of a lot of those prescriptive requirements coming out of those have focused really on the framing components, namely steel stud framing. And I think, we've seen significant kind of ratcheting up, if you will, or increases to the requirements for CI over probably the last, 10 years, 5 or 6 iterations of the code. And that, I think, which really kind of drummed up, of course, a lot of interest and really focus on CI as maybe not so much even kind of an option, almost mandatory in a lot of environments and conditions, and even different parts of the country where it might be required for performance reasons. So we've already probably all seen this before in the past, but the lovely definition of CI, just to kind of lay the ground rules for us here, is insulation that is continuous across all structural members without thermal ridges other than fasteners and surface openings. It can be installed on the interior or the exterior or integral to any opaque surface of the building envelope, and that comes directly from ASHRAE. A thermal bridge, we here at JM use the definition of a thermal bridge as an element in a building assembly with relatively higher thermal conductivity than the surrounding materials, which allows heat to bypass thermal insulation. So it's kind of that short-circuiting effect, if you will, of these structural members, whether it be slab edge conditions as you see here, or the framing components, et cetera, that are kind of creating this physical connection through that wall assembly, right? And that's really kind of what we're talking about trying to control for when we're talking about continuous insulation. And it really is what's happening there is it's that conduction effect. And that is, conduction is heat transfer by direct contact, by physical contact. So if you have this physical structural component moving all the way through that wall system, now you've kind of got this physical connection from your interior to your exterior. And that is a very efficient method of transferring heat in one direction or the other. And of course, again, kind of having a detrimental effect, the opposite really of what we're trying to control for when we're talking about, minimizing thermal transfer through a wall system. A couple other examples for you here. Again, kind of a slab edge condition there on the left. That's a fairly famous building out of Chicago, the Aqua Tower there. Got a roof system there in the middle. Kind of got some issues with those joints, those seams. Looks like some water intrusion there, creating a conductive effect through that system. And then a girt system there on your right. So again, kind of a lot of common attachment methods, design methods that we use can be extremely detrimental from a thermal bridging standpoint. And of course, we can't forget about, of course, the stud framing in wall systems as well. And we think about whether it be wood studs, steel studs, when we start adding up all those various framing components in that wall system, additional support around windows, doors, penetrations, et cetera, those framing components can easily total up to 25% or even more of the wall area. So I think, the general kind of thought process with insulation, of course, is it's kind of this, positive 1 + 1 = 2 relationship. Well, the reality of it is we're not putting insulation in every portion of the wall. Maybe only 75% or even less of that wall even gets insulation within the stud cavity. So continuous insulation aside, I think we can see here that, just cavity insulation by itself might not be the best solution for creating a good thermal resistance in a wall system. Some other pain points here to think about when we're talking about, just a standard framed wall assembly. Excuse me. Corners, of course, again, we mentioned kind of framing around doors and windows. any areas of the wall where you're going to have multiple structural components kind of stacked up next to each other, and even potentially in closets or behind furniture, where you have poor airflow. And again, if you're having these kind of conductive thermal bridging effects occurring, these tend to be the pain points, the common problem areas where you start to see issues related to either condensation, of course, and kind of the cascading effect of that condensation. And if that wall's not able to kind of dry back out or warm back up and compensate for that condensation, then we risk, potential for mold, potential for rot, structural degradation, interior air quality as well. So again, just kind of, if you have thermal bridging occurring, these tend to be some of the areas where it can be significant enough to actually start causing interior indoor air quality problems. So we looked at a number of examples so far. Now let's kind of look at some of the numbers, if you will, behind thermal bridging. And I think this is kind of a good, not even segue, but impetus for what, energy codes kind of, considered over the years and why they've, of course, been asking for additional CI requirements in the various iterations over the last, decade or so. So kind of give you a quick breakdown of what we have here. Essentially a fairly simple wall assembly. We have a wood framed assembly, as you see there at the top, and a steel framed assembly, and of course a bunch of kind of standard components that we're including in a typical exterior wall system. And we're taking a couple of different section cuts through that wall. So just starting off with the middle columns here, the wood columns, we're basically taking 2 section cuts through that wall assembly, one right at our framing component and then one right at our cavity section in our wall system. And these are all R values. These numbers in this table are all R values, except for we do have one U value calc at the bottom there, which I'll get to in a second. But as we kind of just walk down the various components of the wall system, you can see on average kind of typical R value associated with those various components. Air film, outside air film, essentially paint, whatever our cladding system is in this case. No continuous insulation on the assembly at this time. Exterior sheathing, framing components. So in this case, with a wood frame, a wood stud, you're getting, roughly 4.5 R value out of that wood stud. So, decent kind of R value there. Of course, we don't have any cavity insulation at that framing component. Interior gypboard, interior air film, of course, paint again. We total up the R value of that assembly right at the framing component, and that totals up to an R value of 7. Move over, section cut through our cavity system there. All things held equal, except now we're taking a section cut at the cavity. So instead of having a framing component, now we swap that out for cavity insulation. In this example here, just call it R13. We total up all the R value of those components at the cavity section, 15.5. Now, we're going to convert to U value first because U value is actually a better measure of total wall performance. And then we're going to convert back to R value really just for example's sake because we are using R values in this table, and R values tend to be kind of more of the common a number that people understand better. So in order to get to our U value calculation, first I want to tell you that U value, if you don't already know, is measuring transmittance. So it's essentially measuring the opposite of R value. R value measures resistance to heat flow. U value is measuring transmissiveness of heat flow. So it's essentially the inverse of the R. So the way we get to our 0.08 there, quick little math equation for you is going to be, we have our cheat, kind of our cheat equation up here in the top. If you can see my little red highlighter button here. So again, it's the inverse of the R. So it's going to be 1/7 times 25% of our wall, because we said, in this case, we're assuming 25% of our wall is framing, plus 1/15.5 times 75% of our wall. So again, 1/7 times 25% plus 1/15.5 times 75%. You do that quick math equation and you would get 0.08. So that is the transmissivity of our wall in total. So we combined all those kind of section variations together and we got 0.08. Well, if we flip 0.08 back into R value for the sake of the demonstration here, the effective R value, that total assembly in total is 11.9. So we put R13 in the cavity, we're only getting a total performance of 11.9. So in general, kind of, you would assume, again, that positive relationship as you add all these components together, you're going to get performance of better than what you actually put, the R value of the insulation you put in the cavity. But with the fact of thermal bridging, wood framed assembly, your total performance in this case are 11.9. So not a huge drop off. Move over to those last two columns there. All things held equal, except now we have a steel stud in there, and you can see the R value of that steel stud significantly lower than the framing component, and of course, much more highly conductive. So 0.69 in this case, we total up all those components there, we're at 3.2. Of course, our cavity didn't change. We redo the math here in this case, and now we get a total R-value performance of 8.1. So again, we put 13 in the cavity, but now based on the thermal bridging conductive issues with the steel stud, you're only getting a performance of roughly half that. And that's kind of what a lot of studies and tests have been done out there related to steel stud framing. Generally, you're looking at a 40 to 60% loss in your R-value performance with a steel framed assembly that's not thermally broken. So that shakes out pretty much right in line with what other studies have shown. So again, significantly detrimental to a wall system. So of course we want to talk about how we remedy that issue, right? And continuous insulation, of course. So a couple examples of the most common materials being used for CI on the market. Rigid foam boards, of course, both in wall systems and used on the roof. Spray foam is another material that we're seeing a growing market share as a good option for continuous insulation, typically done more in Canada at this point. And then, of course, mineral wool, another one that we've seen gain actually quite a bit of traction as a CI material in recent years as well. So breaking these down just a little bit further, kind of into some of the subcategories of the various materials in this case, rigid foam boards, a lot of different kind of products on the market. Manufacturers really kind of three material makeups: expanded polystyrene, extruded polystyrene, and of course polyisocyanurate. Closed cell spray foam actually falls under that polyiso group, so it's under the thermoset kind of ISO category. Mineral wool, of course, its own category. And then there are some other kind of specialty, if you will, products out there. Of course, EIFS systems, stucco systems, or full-on systems that typically incorporate some level of continuous insulation into them. Structural insulated wall panels, insulated concrete forms, again, kind of specialized systems that do incorporate some level of continuous insulation into them. So breaking down here in this case, the call it the most common kind of performance metrics, if you will, performance criteria that we're often kind of maybe looking at when we're trying to decide on one material or the other. Now, I'm not going to run through every single cell in this table in detail, but again, you see there across the top, we have EPS, we have XPS, polyiso, kind of your typical foil-faced wallboard, CC spray foam, closed cell spray foam, and mineral wool. Now, if you think about, a lot of the kind of the functions we're typically looking to, to exterior walls to provide, we can kind of go down the far left column there, drainage planes, vapor retarders, air barriers, what the kind of typical R value of the material is. And again, not going to run through all of these, but if you kind of look across the table here, a lot of these products can actually serve other purposes beyond just the thermal performance, right? We kind of alluded to this early on in that we'll dive into some of the other beneficial aspects of including CI into a system, kind of beyond just the additional thermal performance and that break in that thermal bridge. It can actually do a couple other, other things for you. And you can see here, some of the products can of course be used as certified air barriers, as long as you're kind of taping and sealing the seams. Various perm ratings there, kind of depending on, of course, maybe what perm rating you're looking for in relation to other materials you have included in the wall system. One last thing to touch on this slide being fire performance. So you can see there at the bottom, we kind of color coded it as kind of good, better, best, if you will. Expanded polystyrenes tend to be the worst from a fire performance standpoint. Your polyisos and closed cell foams, the thermoset materials tend to be a little bit better. And then, of course, mineral wool really being non-combustible and, completely on another level from a fire performance standpoint. That's pretty much all I was saying here. Again, is just kind of a good snapshot of these various materials, how they kind of pan out amongst each other. And you can see there, based on what you might want out of the material, kind of what one may be better or not so good from, in relation to the others. So with that said, of course, CI applications, pretty much at this stage in the game, there's really no limitations as far as, what type of veneer, what type of structural system. They function well really in all types of systems, mass systems, of course, frame systems, even metal buildings. We see CI being done. It can be done on the interior. Typically, that's more of a manufacturing, industrial, fulfillment center type application, but we do see that done quite a bit on a lot of those type of uses. Of course, traditionally here in some of the pictures you can see, incorporated, of course, kind of in that exterior cavity portion, the drainage portion of the wall system. And again, really no limitations, whether it be panelized systems, of course, masonry, brick, et cetera. And we'll talk a little bit about more of some of the attachment methods out there that can be used within these systems to, again, maintain that thermal break. So back to our lovely math equation here. In this case, showing now that we kind of touched on the basics of CI, let's again look at some of the numbers behind kind of the beneficial aspects of those. So this is our lovely assembly here we had before. In this case, wood framed assembly. We're at 11.9 there in the middle. We move over to those two columns on the right, and now we add, in this case, 3R of continuous insulation to the exterior of that system. It's very small, half-inch of rigid foam board in this case. So you can see now we're at right at our framing section, we're at an R value of 10, cavity section, R value of 18.5. We redo the math in this case, and you actually get, now you see there at the bottom, a total R value benefit, we're up to 15.3, and we got an R value benefit of 3.4. So we put 3 on, and we actually got a benefit of 3.4. So that's a pretty significant return on investment from an R value standpoint. And the reason for that is because it's essentially, when we add CI to a system, it's kind of a twofold effect. Not only are we adding this additional thermal resistance, but we're also breaking that conduction, we're breaking that thermal bridge. So it's, again, it's a twofold kind of benefit, and that twofold benefit translates to an overall R value benefit of essentially greater than what we put on the wall system. So as you can see there from a numbers standpoint, pretty nice return on investment. Looking here at our framing, steel stud assembly in this case, that should be 8.1 there at the bottom. And then this would be, that is correct there. This number's a little off, but anyway, not sure what happened there. But nonetheless, the bottom right number, our total benefit on our steel framed assembly is correct, a benefit of 4.5. So we put 3 on, and we got a benefit of 4.5. And again, that's directly related to the conductivity of the steel. So we added additional thermal resistance. We broke that thermal conductivity that was more significant with the steel framed component. And now we've actually got a benefit again of 4.5 with an addition of 3. So as you can see there, the thermal performance benefits of CI are very significant. And that's really kind of, again, some of the impetus and thought decisions behind Energy Code, why they're asking for this material, because it is much more efficient in that exterior portion of a wall system than it is in the stud cavity. So we're going to look at a couple other additional benefits of continuous insulation, in addition to, of course, the thermal numbers that we just ran through and examples you saw there. In this case, related to essentially condensation control and kind of the temperature vapor profile of a wall system. So you can see by our numbers we have here, cold climate outside, we're at 5 degrees. Traditional kind of conditioned interior space here on the inside of our wall at 70 degrees Fahrenheit. So of course, under those basic conditions, you're going to get diffusion across that wall assembly, your warm, humid air trying to make its way across the wall to that colder air. And of course, when under that condition, as that warm air moves along that wall, through that wall system, and it starts coming into contact with these colder surfaces, you can risk condensation inside that stud cavity. Now, if that's kind of under those conditions for an extended period of time, and you're not able to dry out or warm that wall back up to help kind of alleviate those condensation risks, you can get, of course, significant buildup to the tune of actually having detrimental effects on that system. Of course, this is a bit of a, call it an exaggerated example, as you see here, but diffusion, it's a fairly slow process, and I would say, and we don't have any kind of specific numbers tied to that condensation risk, but, if you're under kind of a steady drive for 30 days or more, you can start having significant condensation build up in a wall system. So our section there on the right, we've added this lovely blue line, which is now our continuous insulation in our exterior, over our exterior sheathing component in our wall system there. Now, the beauty of adding the CI is not only are we getting that thermal resistance kind of across the whole wall system, but it warms up all those other materials kind of, from the CI inward. So all these materials are at a much closer temperature to that 70 degrees. So what happens is that as that cold air moves across that assembly, it doesn't reach its phase change, it doesn't reach its dew point until it comes into the surface with that, really the exterior face of that CI. That's where we're finally getting to a cold enough surface that we're going to risk condensation in that assembly. And at this point, we're not really risking condensation because that portion of the wall system is designed to control for liquid water in the first place. So if we have condensation occurring at that stage in our wall, that's fine because that's where we're typically wanting it to land and drain it out of our system in the first place. So kind of one benefit here to show you kind of maybe a little bit clear example of that temperature profile here, in this case, a little diagram from buildingscience.com. Same exact wall system we saw there. Now you can actually see that temperature profile across that assembly, 70 there at the top, and it's kind of we trickled down to 5 there on the exterior. And you can see how fast the temperature that drops across that wall system with no CI. So we go down almost 60 degrees in the same distance that on the image there on the right. When we added CI to the system, we've only gone down 10 degrees. So again, all those materials components CI inward at a much warmer temperature, much closer to that interior conditioned space. So we don't risk condensation at that point in the wall anymore because those materials are much warmer. So we don't risk condensation again until it moves further out of the wall system. And codes actually specifically recognizes that phenomenon we just looked at, and they allow for class 3 vapor retarders on our wall systems in these colder climates. So traditionally, as we saw in that last diagram, you're going to include some kind of vapor retarder towards that warm interior face of our wall to help minimize the effects of that vapor drive, that condensation, to minimize that risk of condensation. Well, if we add CI to the system, we reduce that condensation risk, and we can essentially eliminate that vapor retarder or go down to a class 3, which in a lot of cases is something as simple as latex paint. So code specifically recognizes that. You can see the sections there on the bottom right where it's called out in the IBC. And then just some examples there on the table on the left of the various climate zones, the minimum CI number you need to have over kind of your base wall in order to meet the qualification to go down to a class 3 vapor retarder. So, whether it be, R value of 5 or R value of 7.5 tend to be, fairly common numbers within code, or, jumping up to some thicker numbers there as we get colder and colder climates. But again, adding that CI to that exterior can allow you to eliminate a potential material on the interior face of that wall system because we reduce the risk of that condensation inside that wall system. So now kind of looking at the same setup, but now going the opposite direction. We're warm outside, 90 degrees, very high relative humidity. Again, fairly traditional conditioned interior space. So now in this case, our vapor drive is moving the opposite direction. So now again, we would risk really condensation on the interior, or really the interior face of that chipboard as that warm air moves across the assembly, comes in contact with a cold surface. That's where we can risk the potential for condensation to build up. Well, back to our CI example there on the right, we have our lovely blue line. Now again, all those materials CI inward are at a much closer temperature to that 70 degrees. So again, the first kind of cold condensating surface that warm air is going to come in contact with really now in this case is the backside of that CI material. So if you're under these conditions and you have, again, you're under these conditions for a significant period of time, or, a warm climate where we're under these conditions, the majority 6, plus 9 months of the year, I would recommend putting some type of capillary break in this layer of the wall system, right? Because we know we're going to risk condensation here. And if it's under the conditions where it's, occurring steadily and it's not able to dry back out as temperature change, putting some type of spacer in there can help that water drain out of that system. So whether it be a fluted type board or a crinkle face, polyiso, or maybe even just some literally, type of spacer in there to create a capillary break, that's going to very much help improve the, the functioning of that WRB, our drainage plane layer we have right up against our sheathing there. So again, just something to be aware of there. Warm climates, doing CI in the exterior still shifts that vapor profile outside of the stud cavity, which is where you want it, but other things that may be considered based on kind of where that dew point's occurring. So we'll talk a little bit about air barriers. Again, we kind of alluded to those earlier on in our little table. a lot of those CI materials, rigid foam boards, spray foam, of course, can function as an air barrier as well. And really that boils down to how you're treating, sealing the joints, right? We need to be either, sealing them or taping in some fashion, taping the penetrations, linking those, of course, with our flashings and our other materials to create that continuity, the continuous layer, and those can actually function as an air barrier as well. And I'm really just showing here examples of the three most common kind of pressure drivers that create pressure differentials within a building that are going to pull air through that exterior wall system. So whether it's fan pressures, stack effect, the phenomenon that warm air is lighter than cold air, or of course wind effect, as wind's hitting that one side of that building, that basically creates negative pressure effects on all other sides, and of course uplift on the roof. We really want to try and minimize those pressure drivers or minimize that air transfer through that system in order to improve, again, the efficiency of it, minimize any vapor or temperature drive coming with that air. And those CI materials can contribute to that fact. And if we want to help tape them, seal them up, really use them in a linked fashion with our other materials, they can function as certified air barriers in that wall system. So kind of, again, maybe, again, back to the two birds with one stone idea, in that not only are we getting this thermal resistance, we're getting our thermal break, and now we can also use this material as an air barrier as well. So things to consider there. A lot of the products out there do have ratings and certifications with various bodies to allow them to be used as an official certified air barrier in a wall system. Water-resistant barriers as well. A lot of the foil boards, polyiso rigid foam boards, and even some XPS products can function really as your water-resistive barrier in your wall system. So they can function, as an air barrier and a full-on drainage plane, depending on, of course, how they're tied in with the other components in the wall system. We have a picture of mineral wool on there as well. Mineral wool can't function as the actual water-resistive kind of drainage plane layer in the wall system, but it functions, of course, within that space. So all the exterior grade CI related mineral wool products on the market are treated with some type of water repellency. So water will beat up on them. They will shed water. They're not going to absorb that water, so they can function, of course, within that drainage plane space. And you would, of course, still need to include some type of, traditional WRB membrane, whether it be peel and stick, sheeting, fluid applied, etc. So again, various materials have properties that can do different things. A couple other things to point out related to mineral wool here, aside from the fire performance, which we'll talk about here in a minute, you do get some kind of, call it aesthetic benefits, right? You can see here a couple examples of an open joint rain screen system with some lovely blue board kind of peeking through behind that open joint. Of course, all manufacturers' products, for the most part, on the rigid foam board side, are pretty heavily branded, whether they're color of the manufacturer or labeling, branding, etc. Mineral wool tends to be a little bit more uniform in color. Kind of almost get it in a darker kind of, again, really kind of base uniform type color that's not going to, again, kind of telegraph through a wall system such as this. So just things to be aware of from an aesthetic standpoint. Kind of cladding, fire performance aside, you do kind of get a little bit better aesthetic benefit from that material there if it's some type of open joint system. We do see some ancillary acoustic benefits with mineral wool as well. And just kind of highlighting this one row of numbers in a slide here out of our acoustics presentation. We did some testing with kind of a base wall system you see there in the middle without any continuous insulation. That wall system tested at an STC of 40. We added rigid foam to that same assembly, and it tested at an STC of 40. Rigid foam in general is very poor acoustically, so very good from a thermal standpoint, very poor acoustically. So just something to keep in mind with exterior wall systems. A lot of the green rating systems, LEED v4, well building standard has definitely kind of put a renewed focus on the acoustic performance of exterior wall systems, and the rigid foam boards in general do not perform very good acoustically. And of course, we see there the bottom line there on that row. We added mineral wool to that system, and it performed at an STC of 44. So we did get some kind of supplemental acoustic benefits with mineral wool in that system versus your traditional kind of rigid foam boards. So again, just things to be aware of, performance kind of nuances amongst the different products. Now, we have this slide in here because we typically get a lot of questions about the various attachment methods that can be used with some of the products we just talked about. So just got some various options out there, some of the more common attachment methods that are on the market that can function as a thermal break. kind of bracketed clip systems, I think you'd see there, some traditional kind of Ziegert profiles that are now made fully out of fiberglass. And back to kind of the clipped or bracketed systems, you know, you see that brick ledge and kind of your traditional Ziegert functioning there on the bottom right. We haven't really totally shifted the design of it. All we've done is kind of limit the profile of what's being attached back to that wall. So instead of having the full length of that return flange connected to the wall and running the full length of that material, now we basically are only attaching it right where it's actually, you know, right where it's essentially being attached to the wall system. So we've got a bracket there that's, you know, of course being our structural component, but we're limiting the amount of surface area, the amount of profile of that thermal bridge, if you will, because all these materials typically are pretty highly conductive, made out of metal. Incorporate some type of fiberglass component in there, spacers, et cetera, and you can significantly reduce the thermal bridge profile of those various attachment systems. Talk a little bit about fire control here related to some of the CI wall materials as well. As we kind of showed earlier on and back to our table, some are maybe not so good from a fire performance standpoint, some are, you know, okay, and then of course, you know, mineral wool and some other products are very good. But again, the point here being is that, of course, we need to maintain a means of egress in our structure, and we're going to fall under kind of different parameters based on the height, floor area, kind of the use occupancy classification of our building is really going to dictate what kind of construction type we fall into. So, of course, as we see there at the bottom, types 1 through 4 are really, types 1 and 2 being the most stringent, and types 3 and 4 really asking for some type of non-combustible exterior wall material. So we really need to be cognizant of that, in that if we want to introduce some of these combustible foam products as a CI material into that wall system, we may or may not kind of be restricted to, you know, what we can use based on the building type. So that can be a significant kind of driver in material selection. If we're, you know, in type 1, 2, we might be looking at something that's, you know, have to use something that's more fire resistant in order to meet code compliance. And really the point of all that is the saying that we can use combustible materials in non-combustible type 1 through 4 construction. We just have to basically go through another step of testing, right? So an example here of the NFPA 285 assembly test, which you probably all at least heard of at one time or another. And essentially this test comes into play when we want to introduce a combustible material into a non-combustible building type. And that's kind of, you know, where energy code and building code are butting up against each other. Energy code says, hey, let's put a bunch of foam board into our wall system to improve thermal performance, but building code says, hey, you're, you know, in a type 1 structure, it needs to be fully non-combustible. So the bottom line is, if we want to use that material in a non-combustible building type, we have to do a fire test to prove that we can, you know, that wall system will hold up under, you know, flame exposure for an extended period of time to allow for egress. So without getting too far into the nitty-gritty of that test, you can see there, simulates a fire at a window. It runs, the fire exposure runs for 30 minutes. And if we maintain certain parameters, both in flame spread and in temperature rise, that assembly with those combustible materials now passes that test and can be used in those type 1 through 4 assemblies. Most common kind of trigger points that you see related to NFPA 285 here, and you know, in the context of what we've been talking about so far, WRB systems, foam plastic there, of course, listed at the bottom, and of course a lot of cladding systems out there as well are all going to trigger the potential need for NFPA 285 testing. And of course that's really on the burden of the manufacturers to test their products, test these systems as much as they can to make them available to the marketplace, so it can make your guys' life easier to incorporate these materials and systems into your actual designs. And back to my kind of not all sheathing is created equal here again, mineral fiber, of course, being non-combustible, the thermoplastics, the polystyrenes, versus, of course, our thermosets. A color issue there, but again, thermosets being the second best in that they have stronger chemical bond, which holds up better under fire. So thinking of NFPA 285, kind of your color palette, if you will, of available materials is going to be broader with your polyisos, your spray foams, because there's more test assemblies available because those products are more fire resistant and they're going to hold up better. And by virtue of that, there's a much broader array of already approved assemblies on the market. With your polystyrenes, you're pretty much limited to masonry veneers, precast, things like that. So something to be aware of there. Bit of an issue on our color hierarchy here with the text, but my upside down pyramid is correct. So non-combustibles, mineral fiber, and fiberglass. Thermosets, your polyisos, your thermoplastics are going to be your polystyrenes. All right, so the moment you've all been waiting for, our transition from walls to roofs. So we're going to run through a number of transition slides with you here, and then I will turn it over to Joel to handle the rest of the roofing portion of the presentation. And no stranger here with these type of transitions is that not only do we really want to maintain, of course, the thermal comfort or the thermal continuity of this system, but we really got to consider all the other functions as well: water control, air control, vapor control. And the beauty of a lot of those membranes and those materials out there is that they can really function as all those kind of components. A lot of traditional WRBs are going to give you water performance, they're going to give you air performance, and they're going to provide some level of vapor retarding ability. And of course, really the key here being continuity and compatibility. So we really want to make sure from a QA QC standpoint that we are really focusing on this tradition, the connection here, because this is right where two trades kind of end their work, right? We have whoever's kind of doing the wall system, roofing contractor, they're both kind of terminating right here at this parapet. So just really stress the need for coordination at this stage of the wall system, and continuity as well as compatibility of materials, making sure that they all kind of function, play well with each other, right? Because there's, between the number of brands and all the different product types out there, lots of different options to choose from. And of course, lack of continuity can lead to water leakage, air leakage, thermal bridging, and of course condensation. Really nothing new here from what we kind of saw before. We're just showing a wall system here that's not thermally broken. You've got a slab edge condition that's exposed right there. And you can see by that thermal image there on the right that the end of that slab edge on the right side is green, right? So that's essentially saying that slab edge is cooler than the rest of the slab edge that's red. And then that means we're having conduction thermal bridging occurring at that stage in our wall system. So maybe a little bit better option here. Again, we've run the rigid board all the way up past that exposed slab edge condition there. We've got our WRB, that red and white dotted line in behind that. We're tying that up in and over our control layer there on a roof system, that red and black line, linking those insulation components together, capping it up. And you can see now that slab edge pretty kind of uniform all the way across now. So we've done a better job, in this case, providing that continuity at that transition. And we're highlighting it there. Then it's kind of some other changes, examples here. Again, things to consider. Again, kind of back to the material compatibility thing. If you're not sure of compatibility, we highly recommend that you reach out to the manufacturers to have them sign off on, or at least make some recommendations on. Here's the 3 different brands of materials we're using. Here's our roof system. What's kind of the best you recommend that's going to all work together, play well with not cause additional issues once we stitch them all up and put them on the wall. So rely on your manufacturers if you're worried about material compatibility, for them to help guide you through that process. In conclusion here, again, at least from a transition standpoint, careful detailing instruction, and really again back to the idea of coordination and that understanding where one trade's ending and where trade's picking up is really crucial, and the compatibility of various membranes as we're changing from one system to the next. Again, kind of sequence of construction there, the third bullet down, right? Again, who's responsible for the final connections. And that's pretty much the transition. I'm going to turn over to Joel. I don't know if you have anything else you want to add here, Joel, but I'm going to go ahead and pass the ball to you for the rest of the presentation.
Sounds good. Jeff, can you hear me all right?
I can hear you.
Great, thank you. I think I just did something I didn't mean to. All right, so Jeff did a great job walking us through the walls and through that transition. We are now going to spend the rest of this presentation talking about roofing systems. So let's see. So with commercial roofing, low-slope roofing, there are a ton of different options you have for how you're going to be putting that roofing system and material on, and the type of materials used in that roofing systems. Often we start with the conversation around membranes, as far as is it a mod bit or a single ply or even a liquid roof system, are just some of the choices that you have and some of the many choices you'll have to make as far as putting the entire assembly together to make sure that it meets the project's need, and then also how all those different components transition to that wall and what's happening at the edge condition. As far as the insulation for roofing systems, our industry is primarily using polyisocyanourate as the insulation. It has a lot of great physical characteristics that we'll visit in a moment, but it represents about 80% of what's being used, at least in the U.S. commercial industrial market. There are other products out there that are in use, and sometimes even multiple products, especially when you have a cover board that's included in your roofing system. Cover boards bring a lot of great physical characteristics, strength, and protection to that insulation system, to the roofing system in general, and those can often be different material than polyiso, but there are also options to use high-density polyiso as that cover board. When you think about your insulation system for your roofing assembly, there's a lot of things to take into consideration, starting with condensation. So that's a conversation about a vapor barrier within that assembly, especially when your vapor drive is moving from inside the building to outside. We'll talk more about that. Improved drainage. So are you including tapered insulation as part of your project to improve that drainage on top of the roof? Stress distribution. It's a conversation that circles around the use of cover boards and making sure that that roofing system can withstand the foot traffic, the overburden or things that are put on top of it, such as vegetative systems or patios or other usable space. All materials don't play well with each other, so it's important to know the type of membranes, the type of insulation you're using, the adhesives you're using, and how all of the different components will interact with each other. And that whole roofing system, including insulation, needs to be designed that it meets the fire code requirements for that building and for that roofing system, and wind uplift requirements. And that has a lot to do with the location, the height of the building, and several other requirements that fall into the understanding of that wind uplift requirement of that system. And then all that needs to be balanced with energy codes and the amount of insulation needed to meet those energy codes or the energy efficiency requirements of the building itself, as well as thermal bridging. And just to give you an example of what thermal bridging looks like in a roofing system, a low-slope roofing system, the picture on the right is actually a roof that has a frost on top of it, and you can see the fasteners that are used to hold down the insulation underneath that membrane are acting as thermal bridges and are warming or melting that frost before the rest of the roof. And so it's a real concern with the roofing system and thermal bridging with those fasteners. We'll talk about that in a minute, about what some best practices are to deal with that. So how do you know how much insulation you need in a project? That goes back to your building code, or whatever code has been adopted in your area. That's either going to be an ASHRAE 90.1 or the IECC codes. Different years for different locations, so make sure you understand what code you're working under and what those minimum requirements are. Those values can be used not only to meet the code, obviously, but also in your energy calculations and your project economics, and to try to figure out if it's the minimum amount of insulation you want or more. And there's plenty of projects that do dictate more insulation. A good example of that, Jeff mentioned cold storage buildings earlier, and so that's a great example when you do want to have more insulation than a typical project. The way ASHRAE determines the minimum amount of insulation needed, or R value, is through dividing the country or the area up into different zones. Those zones are dictated by the number of heating degree days in that area. So as you move further north, there's more heating degree days and a higher R value is required. I sit in Colorado, and so we're lucky here. We get 4 different zones that we have to deal with depending on how high in elevation you are. So it's really important, especially for us and, well, for everyone, to understand what your zone is that you're working in and what that code requirement is. This is what that would look like in your ASHRAE 90.1, or rather this is from IECC 2015, the table. You'll find similar tables in 90.1. It'll divide up that R value requirement based on the zone, and also about how the insulation is being included in your roofing system. There are opportunities to put it below deck. The table or the chart you see here is for insulation above the deck itself. There's also in the code some exceptions for tapering, and it allows for the ability for you to taper down into your drains and sumps, and it gives you some guidance of what that should look like. In general, we typically or traditionally talked about insulation in either high or low thermal values. The insulation we're just talking about, polyiso, expanded, extruded polystyrene, all sort of fall into that high thermal value, that high R value. But there are plenty of other materials that are used in your roofing system for cover boards and other components that should be included in your insulation calculation, your R value calculation. They may not add quite as much as those high thermal values, but can make a big difference if you're really trying to fit that high R value into a tight space. So moving on to another issue with your insulation package, and that's dealing with condensation within that system. Thermal drive from inside of a building to out can cause damage to the insulation system itself and that roofing system. If condensation hits the dew point as it moves through your insulation, it will condense. It will destroy that R value or reduce that R value. It can cause mildew and mold issues. It can cause early failure of that roofing system. And if it's bad enough, it can even start more or less raining back down into your building. So it's really an important issue to understand where your vapor drive is coming from, and if a vapor barrier is needed to protect that roofing system and the building from condensation. So this is a diagram. You have, obviously, there are some nailable and non-nailable decks. So a concrete deck you can put a vapor barrier directly down on, or a nailable deck such as a steel deck. I think best practice is to start by mechanically fastening down a thermal barrier. So this would be a gyp board per se, or something along those lines, and then adhering your vapor barrier and adhering everything else above that. That way you don't have penetrations in your vapor retarder, your vapor barrier, which can lead to it not performing the full capacity that it can. So what you see here is one option, which I think is best practice for your steel decks. Some rules of thumbs for if you're going to include a vapor barrier in your roofing system. If your January mean temperature is less than or equal to 40 degrees Fahrenheit, and then particularly, this should say interior relative humidity greater than or equal to 45%. So your natatoriums, your industrial kitchens, anything along those lines, definitely consider a vapor barrier, vapor retarder in your system. Now, if you are including one, what you want to do is install a vapor retarder that is a class 1, also known as a vapor barrier, and that's anything with a perm rate of 0.1 or less. All right, so there's a lot of different insulations in use today. Polyiso, as I said, dominates the market, but extruded and expanded polystyrene are also in use in roofing systems for particular uses, as well as sprayed polyurethane. One of the issues with polyiso is that it has a blowing agent that creates those closed cells in the manufacturing process. That blowing agent will migrate out of the insulation over a long period of time. And so we've had to sort of switch over from an R value to represent the resistance to heat transfer to an LTTR, or long-term thermal resistance of system to give you an average of that R value as it changes over time as that blowing agent migrates out. What this table demonstrates is that that LTTR value actually is a little different depending on how thick the board is, and that's because it takes longer for that to migrate out as the board gets thicker. We have a lot of different options on how to put the system together or your insulation together. You can mechanically fasten all of your insulation down. You can mechanically fasten part of it and then adhere part of your insulation above that, or you can adhere the whole thing using either urethane insulation or hot asphalt. A lot of different options, and all within are good options, bringing different characteristics to the table. Because your mechanical fasteners that go through your insulation act as thermal bridges, I think best practice is if you are going to mechanically fasten down, and there's a lot of great reasons to do that, great uplift characteristics, it's a cost-effective way to put your roofing system down. If you are going to include mechanical fasteners, I think best practice is to mechanically fasten down your first layer of insulation and then adhere the next layer and all layers above that. What that does is it stops that thermal bridging before it can go all the way through your system and really providing the full value, R value. There's been studies that have shown that fasteners in your roofing system can degrade or reduce that R value of the roofing system by 15 to 30%, depending on how dense that fastening pattern is. So it's really an issue we need to pay attention to and think through when putting together your insulated package. We don't have to deal with framing the same way that Jeff has talked about with the walls, except maybe around the perimeter. So we do have nailers, wood nailers that go around the perimeter of the building that are designed to connect our roofing system, to secure our roofing system around the perimeter to that structural wall. But that acts as a thermal gap, or a thermal bridge rather, just like Jeff was talking about with his walls. One option we do have out there are metal cleats or metal tees that can replace that wood nailer. Therefore, you can bring the insulation all the way to the edge of the building, getting rid of that thermal bridge. Another view of that, you can see how those cleats are mechanically fastened down to the wall itself, and then the insulation can come all the way to the end, getting rid of that thermal issue around the perimeter of the building, which can be quite substantial and definitely worth paying attention to. One of the things I would say, and this is true for I think Jeff would say also, is it's really important to have good details in your plans to make sure that the installers understand what you're trying to do, what those details are, and that covers not only, you see in the middle of the screen there, the fastening patterns around your field perimeter corners need to be taken into account if you have a parapet wall or if you have a lower wall that requires some type of edge metal or fascia. All that really needs to be detailed carefully in the plans. A lot of the details can come from your manufacturer. There's some third-party resources through industry groups, associations. All have different types of details that can be used to help explain how to keep that continuous insulation and that connection from working correctly. All right, so just in summary, we've covered a lot of ground here. We talked about thermal bridging for the walls and roofs. We talked about continuous insulation going up the wall and that connection from wall to roofing system and then the roofing system itself. There are different materials, there are different ways of putting together your wall and roofing system. All that should be taken into consideration and make sure that it's compatible with each other. And that really covers the different types of the water and rain barriers, your air barrier, and your thermal insulation. So I'm going to hand the ball back over to Kim, who is going to finish with some resources for you.
Actually, Joel, I'm not going to finish with resources because we are right at the hour, so we're going to go ahead and jump to questions. We'll answer questions for 15 minutes, If we don't get to your question today, you can expect an email from us. We will reach out to you directly and make sure your question does get answered. So with that, I do want to put one thing up here on the board. If you'd like to contact us, or if you have any questions where you'd like to speak with someone specifically, if you're working or you have questions on building insulation, on the left there you'll see our Tech Connect, the phone number for our Tech Connect team. On the roofing side, you'll see the phone number for the roofing team. And so different phone numbers, different emails, jot those down. They'll be a great resource, and they'd be happy to help you with any questions that you may have. So I'm going to go ahead and kick us off with the first question, and that is for you, Jeff. And that is, can you use a 2-inch perimeter insulation over existing wood siding for a commercial project?
I would say most likely yes, really just depending on, kind of back to the whole, fire code thing, right? Is it, what's the, parameters of the structure as far as code requirements? You could put polyiso over the top of that. A lot of different cladding systems can go over that. Depending on the height of the structure, there's a number of exceptions related. From just a pure functionality standpoint, there's really no issue there. I would say it really is going to boil down to the building type, the height of the building, and the cladding you're putting on. And all of those are going to be drivers that are going to run up against NFPA 285 requirements, where you may or may not have approved assemblies related to, available based on the combination of materials. But from a functionality standpoint, I don't see much issue putting, that over that. And of course, whatever your veneer system is going to be over the top of that.
Thank you, Jeff. And a quick note for the audience, we will post a recording of this webinar and the questions online. We'll send you an email so you have direct access to that as soon as that is live on our website. And another thing is everybody who attended today will get a certificate of completion in your email. If you registered using your AIA number, we will submit that for you. If not, you can self-report using the certificate of completion. So the next question is, I don't know if this is for Joel or Jeff, but I'll raise it to both of you, and that is, can EIFS base coat be applied directly over XPS?
I'll handle that one. Again, that's kind of, I would say yes, kind of generally speaking. There's so many variations of EIFS out there. Traditionally, I would say in most cases you're putting some type of reinforcement layer, whether it be a fiber mesh or a lath system, up first over that XPS board, and then you're putting your base coat kind of on top of that. That's, I would say, in my experience, the more kind of traditional EIFS system there. But there's so many variations out there now with all the advancements in technology with the various modified polymers and things. I would be shocked if there wasn't numerous systems out there that manufacturers have that allow you to apply a base coat directly to the XPS.
All right, thank you, Jeff. Joel, would you like to add anything to that?
No, I'm good, thank you.
All right, excellent. Is this type of insulation effective in weather-changing conditions, for example, from sun to hail in short periods of time?
I'll take that one, Joel.
I might have missed one. Go ahead, Jeff.
My first impression on that question is, as long as you've got an air gap in the system, you're fine. You could have drastically changing temperatures, and of course you might risk, some condensation effects in there. But if you've got, a proper air gap in there, that's the key. That's going to allow any condensation water buildup to drain out. That's going to help provide ventilation, some drying effects, any kind of, again, condensative effects, allow your flashings and your drainage materials to function properly in that system. So I would say absolutely, as long as you're maintaining, proper air gap in that space in the wall.
All right. The next question I have is, what is the leanest insulation assembly available to achieve an R39 roof for a residential structure? And I'll hand that to you, Joel.
Thank you for that. I have to admit that we don't deal with residential structures or residential roofing. We're mainly dealing with flat and low-slope roofing systems. So I'm not sure I can answer that question.
That's a fair answer.
I'll chime in, Joel. The leanest and the thinnest profile insulation material that's going to get you to that number is going to be spray foam. closed cell spray foams 7 R per inch, in some cases higher than 7 R per inch. That is going to give you your most insulative bang for your buck in the thinnest profile. A lot of kind of caveats to that related to, again, fire code and things of that nature, but from just speaking to that, directly to that question, spray foam, closed cell spray foam would be your best product.
All right, thank you, Jeff. The next question I have is, what is the best way to determine the thickness of polyiso needed for a minimum R value requirements on a fully tapered roof system?
Now this one I can take. So my best suggestion would be for you to send your plans into a tapering department. A lot of your manufacturers have complementary tapering departments, including JM. They can provide you not only with the best options for that taper design, but also that minimum, that maximum, and average R values associated with it. You can include that, you can put that in before you go out to bid and include that information in your bid package. That will give you much more consistent results from the contractors bidding on your project.
Thank you, Joel. The next question is for you, Jeff, and that is, are there areas where you should not use fiberglass or mineral wool?
That's kind of a fairly broad one. I would say, I guess back to kind of what's the energy code requirements in your area, right? If it's, fairly stringent, you might be better off with something of a higher R value, especially, of course, in a roof system. You're getting a lot more R value, bang for your buck with a rigid foam board. And just in general, fiberglass mineral wool is about 3.5 to 4 R per inch. Foam boards, 5, 6 R per inch. And then even some of the other foam products a little bit higher. So, I would say from a continuous exterior standpoint, as we saw, there are mineral wool options, for CI. Really not a whole lot of fiberglass options. Not to say there won't be, maybe some of those showing up on the market here as we move forward. But again, I think those traditional products definitely better from a fire performance standpoint. Somewhat limited maybe from on the exterior in that you're really only getting thermal performance with them as opposed to a foam board that can kind of do a lot more than just provide thermal resistance. But then again, they kind of have the fire concern there. So I would think there's, kind of a lot of different things to consider. And I kind of getting back to the, a plug for what we see there on the screen. JM's got so many different products that we really are, pretty agnostic as far as recommendations. We don't make just one product. We make essentially, the full gamut really across the board. So really, can make a lot of recommendations based on, different performance criteria.
Thank you, Jeff. So the next question is again for you, Jeff, and that is the NFPA 285 the primary means for determining the fire rating of a wall assembly?
I would say no. The fire, I guess as far as if you're testing a wall assembly, the ASTM E119 is kind of the standard. So this is another one that comes up quite a bit, so it's probably a good time to answer kind of the distinction here. Your traditional kind of hourly rating that you might find in a code requirement that says, okay, we're in proximity to another structure based on height, we're right up, right up on against a lot line, etc. Code's going to require, probably a 2-hour minimum rating for that wall system. So that 2-hour rating is derived from the ASTM E119 fire test. So that essentially measures flame temperature rise across that assembly over a period of time. If the longer that assembly resists that temperature rise, the longer the rating. So 1, 2, 3-hour rating, etc. UL does a bunch of that. They have their UL 263. It's basically the same thing as an ASTM E119. E119 could be done by any, testing body out there as well. I think UL's, definitely kind of the bigger, the main player on the market when it comes to hourly ratings. But that's essentially if you say, oh, I have a UL design that's an hourly rating, that's essentially what they're doing. They're running the ASTM E119, and then you're getting a rating based on that performance of that assembly. That is completely separate than NFPA 285. 285 only comes up when you're introducing combustible products into a non-combustible building type. So they are not kind of
interchangeable, if you will. So if an assembly is tested and it meets NFPA 285, it does not have an hourly rating. It simply says we had a combustible material in this non-combustible wall type. We ran this test and it measured and it passed. And that, again, that's measuring flame propagation, flame spread via the exterior wall assembly over a 30-minute period. So definitely a distinction there. In a lot of cases, depending, you might have to have both. So you might need to meet a 2-hour rating based on the location and proximity to another building, and you might need, NFPA 285 if we're introducing, metal cladding or something, in there that's going to trigger that requirement. So that's a common question. They are completely separate kind of tests, and they're not interchangeable. If you have one, you do not have the other.
Thank you, Jeff. The next question is for you, Joel, and that is, what are some best practices detailing roof systems to walls, especially in regard to maintaining FM perimeter attachment and maintaining CI?
Okay, so FM is Factory Mutual, and it's an insurance company that we often use as a reference to make sure that roofing systems and the perimeter are done correctly based on fire, wind, and even hail resistance. So for FM, the way they detail their perimeter attachments is they provide a data sheet. It's 1-49 for perimeter flashing. And there surely shouldn't be any conflict between that and continuous insulation on that perimeter, with maybe just the exception that with the perimeter flashing, FM is going to require a number of fasteners, right, to make sure that that edge metal is and flashing is done correctly. The more fasteners in that area, the more thermal bridging, and so that might be a connection to this too, but in some ways that's unavoidable. Some of the things that best practice you might think about is, again, trying to get rid of that wood nailer, replace it with other technology that gets rid of that thermal gap. Think about foaming in all around your perimeter, around penetrations, all gaps within that insulation system, because your insulated board is a rigid board, and there's going to be small gaps which, in irregular shapes. So foam is a great addition in that case. You might also think about redundancy in your systems, using turn bars, using mastic, using redundant types of material to make sure that the thermal barrier and the water barrier are really secure over the life of the project.
All right, and I'm going to say this next question is going to be our final question today, and it is for you, Jeff, and that is, please address what JM is doing for the NFPA 285 for non-mineral wool insulations.
Yeah, so I kind of alluded to that earlier on too, with the various materials out there, your XPS, your EPS, your polyisos, your spray foams that are going to trigger an NFPA 285 requirement. That's on the burden of manufacturers essentially to make their product as available as they can by testing as many assemblies as they can, and that's essentially what it boils down to. There's no kind of standardized third party that we put everything through and they certify it. It's, us saying, hey, we want to test all these different systems and make and we, assuming we pass them, we make them available to the industry to say, hey, this product can really be used in as many different, assemblies as possible. So we're doing testing all the time. I know we had a number of tests scheduled this summer, and I'm not quite sure how many of them went off with the whole virus thing, but again, all the major manufacturers are constantly testing to make those products, essentially as available as they can within the parameters of NFPA 285. So again, and once we test something, we issue an evaluation report that says, basically, I like to refer to it as a kind of a choose your own adventure, if you will. So there's a big table in most of those reports that says, here's all the different combinations of systems, brands, material types that can be used in combination with, polyiso, for example. So you list your base wall, your different types of, type X gyp you can use, whatever your stud wall configuration is, what all the different WRB systems that are compatible with our product, fluid applied, peel and sticks, et cetera, and then all the veneers, right? And the veneers are kind of the one that's, I would say, the final frontier of all the testing, that we've kind of figured out all the other stuff. And it's really the claddings, the metal claddings, the terracottas, the ceramic type stuff, some of the newer, the terracotta is pretty fire resistant, but of course, all the different types of metal panels, ACMs, MCMs, et cetera, the fiber reinforced phenolic panels, things like that. Those are really kind of the ones that I would say separate certain manufacturers from the other as far as do they have those approvals through NFPA 285. So some may, some do, some don't. But those are kind of, I would say, where you run up against the most challenges if it's some, more highly flammable cladding system. You might be more limited in your, available options from a manufacturer standpoint on who already has the testing approvals for, that type of cladding.
Great. Thank you so much today, Jeff. Just a quick reminder, you will receive your certificate of completion in your inbox by next week, next Tuesday, I believe. And then if we did not answer your question live today, we will reach out to you privately in an email to make sure your questions do get answered. So you please keep an eye on your inbox for that. And then we will also send you an email once the recording of this webinar is live for you to watch on demand. So other than that, thank you everyone for your time today. I'm sorry we took you right up to the hour and then 15 past, but we appreciate you staying with us. And if you have any questions, feel free to submit those in the survey afterward. We'd be happy to answer your questions in the survey as well. Or if you'd like someone to contact you, you can also indicate that in the survey. So otherwise, have a great weekend, stay safe, and we'll be with you in another couple months with more webinars.
Thank you.
Thanks, everyone.